Our project is on the impact of large storage dam materials by Jonathan Cook,
Marisa Davini,
Anthony Hewitt,
Marissa Jane,
and Marco Molinares.
Studies have shown that the life cycle of concrete produces a significant amount of CO2. Because of this, we thought that a concrete substitute would be worth researching, since we're engineers and we want to solve problems and share our results. The reason we are doing this study is to identify the local and global impacts on the environment and the economy from construction materials, specifically concrete. In an application, we intend to take the results of the materials impacts and inform engineers, specifically the American Society of Civil Engineers, the EPA, and materials researchers, so that they can better design the future. Part of this is evaluating a triple bottom line, which was evaluated using sustainability metrics. We chose multiple sustainability metrics to research and compare. These important topics include emissions such as CO2 and other greenhouse gas emissions, along with toxic emissions. Other impacts we looked at were impacts on climate change. We included research on economic aspects of the project as well. This includes the recycling rate of the materials and the all-important cost of the project.
An alternative to traditional Portland cement concrete dams could be Plastermax, which is a product of the company Gigacrete. It's a feasible alternative for concrete since it has about half the carbon footprint of Portland cement by applying green technology to create new levels in performance. So how we propose to use it would be to use 10-foot polystyrene foam cubes shown in beige with a 3-inch thick Plastermax layer coated in between the cubes shown in red, which is ideally how you would lay bricks. Then once the dam was to the correct height and width, pilings would be inserted all the way down to the bedrock for stability, which is shown in gray.
The life cycle inventory is established to cover a 100-year period. Some of the main components being considered for Alternative 1, Portland Cement Concrete Dam, are Portland Cement Concrete, rebar, and turbine material. On the other hand, Alternative 2, an EPS and Plastermax structure, consists of main materials such as fly ash, Gigacrete, powder, polystyrene foam, and turbine material. For both cases, the operation and maintenance costs were assumed to be 2% of all installed costs. Now we'll briefly cover the life cycle assessment and life cycle cost analysis for the two alternatives. Impact categories to be focused on are climate change, human toxicity, and fossil depletion. In the chart, the Portland Cement Concrete Dam is indicated by gray columns, while the EPS dam is indicated by yellow columns. The recipe midpoint comparison indicates that the EPS structure is nearly 3 times impactful on climate change, however, has significantly less of an impact than the Portland Cement Concrete structure for human toxicity and fossil depletion. Looking at the life cycle cost analysis, both alternatives are fairly equal. The Portland Cement Concrete Dam has a life cycle cost of $1.82 billion, while the EPS alternative has a life cycle cost of $1.67 billion. Between these two alternatives, there is only about an 8.5% difference.
We performed a sensitivity analysis with the cost data we collected on the two alternatives in order to determine which option is superior. As you can see in the table, we took the total construction cost and the total operation and maintenance cost for each alternative and assumed an interest rate of 6%. We set the lifetime of Portland Cement Concrete Dam to 100 years while varying the lifetime of the Plastermax and polystyrene foam dam. As the graph shows, the present worth of the cost for a PCC dam is higher than that of the alternative dam after its lifetime exceeds 20 years. Since the sensitivity point is much smaller when compared to our expected lifetime of 100 years for the dam, the present worth is not very sensitive to the lifetime in years of the dam. This is because the estimate would need to change by 80% in order to change the decision of which alternative is the better choice.
This project's main purpose was to analyze the impacts of the construction of a large dam in an environmental, social, and economical aspect. The data shows that when it comes to alternative construction materials, the use of a more environmentally safe cement is not only more economical, but has a lower CO2 emission level. The results of the life cycle assessment and life cycle cost analysis show that using plaster max instead of Portland concrete is a feasible alternative. The use of the latest hydroelectric turbine technology also plays a big role regarding the sustainability of the project. Although the cost might be higher, turbines with a large efficiency percentage can generate more power while lowering the energy consumption, operation and maintenance costs, and overall lifespan of the machine. Another recommendation for this particular project, not only on an environmental but also social and economic level, is to aim towards staying local. For example, using materials that can be acquired as close to the construction site as possible will lower emissions when it comes to transportation. In addition, it can cut down the time it takes for the project to be completed, lowering the effects on the surrounding environment of the site. Socially speaking, using local materials and local contractors help the economy of the particular area, which automatically benefits the population. Engineering is responsible for making things better and more efficient. And at this day and age, focusing only on the economic and profitable aspects of a particular design can lead to negative impacts in other areas. Therefore, it is on our best interest to continue researching and finding better ways to use technology in a more sustainable manner for our future and the future of the next generation.